I want to give it a little overview of file descriptors and talk about how they relate to our socket programming conversation. So what is a file descriptor? You've all heard of file descriptors and talked about file descriptors in some of your programming classes, I hope. A file descriptor is really a positive integer that uniquely identifies a file. So every process has a file descriptor table in part of its memory for the process. And the file descriptor is just an index for that specific file in the file descriptor table. And the entry in the file descriptor table for files contain an entry for every open file in that process and some additional information about that file in the process. There are 3 predefined file descriptors. 0 is standard in, 1 is standard out, and 2 is standard error. So when you open a program open a file in your program, it actually gets file descriptor 3 for the first one. The second one would be 4, etc. And those integer values are used to index into the file descriptor array to obtain information about the file. One file can be opened more than one time in a program, and therefore they would have multiple file descriptors if it's for every time that it's opened. Each file descriptor has its own set of properties, such as the file position pointer, permissions, etc. The file position pointer is a pointer that maintains a process's position in a file. So what's the current location where you will be reading or writing for that file? Some programming languages such as C and C++ also have file pointers. A file pointer is of type file, capital letter F-I-L-E, and the file pointer points to a data structure called a file structure in the user area of the process, and then the file pointer points to the file descriptor. So in C programs, files can be represented by either file pointers or file descriptors, depending on what functions you want to use. So certain functions, the ISO C functions, the ISO standard, use file pointers like fopen, fscanf, fprintf, and the UNIX I/O functions such as read and write use file descriptors. So this is what the file descriptor table looks like. Actually, again, 0 is standard in, 1 is standard out, 2 is standard error, 3 would be the first file that's opened by your program. And they ultimately will point to an internal data structure for those files. With the socket API, it adds a new descriptor for network communication called the socket descriptor. But the socket descriptor is also stored in the file descriptor table. So you will notice in this diagram, it's actually called a descriptor table instead of a file descriptor table. Many textbooks and programmers still refer to it as a file descriptor table, but it really can contain more than just file descriptors. And what we will be using in this class for some of the programming with sockets will be what's called a socket descriptor. Again, I mentioned a file pointer. The ISO C function calls actually return a file pointer, which is capital file pointer. And this file pointer points to a data structure that holds information necessary for that specific I/O library and those specific functions. And then one part of that structure is a pointer to the file descriptor entry. So you can see the fopen call is going to return a pointer to the file pointer, which points to this file structure. And then one entry or one value in that file structure is the file descriptor. So it points to the file descriptor table or the descriptor table. There's a few other tables that I wanted to mention that are maintained by the operating system when you're dealing with files in a process. So the file descriptor table or the descriptor table is one per process. And it contains some information about the file, including an entry to the system file table, or sometimes referred to as the open file table. This table is a kernel table, so it's shared by all processes, and it contains an entry for each file open in all programs. This entry also contains the file offset and some other information about that file, and that will become important when we talk more about when we look at our processes and we're forking processes and what's shared and what's not shared, when we talked about processes and parent and child processes, remember that we said if you open a file prior to doing the fork, both the parent and the child share that same file pointer or current file position. And it's because that's maintained in this open file table, which is kernel and shared by all processes. And the file descriptor table is copied from the parent to the child, so it has that pointer and that file open and that pointer information already. Another kernel table for open files is an inode table or an active inode table, and it contains an entry for each active file in the file system. It's actually an inode, so on disks, every block on disk or every file on disk has an inode number associated with it. So whenever one of those files on disk is opened, an entry is put into this inode table or active inode table. And so we open a file on disk, we put an entry in the active inode table, then we put an entry in the open file table, and then we refer back to the descriptor table. In this picture, you'll notice that the file table, 2 entries point to the same inode table entry. So perhaps 2 different processes open the same file, so they're going to point to the same thing. It's also possible to have multiple entries pointed to the open file table. Again, a parent forking a child process. If the file is open prior to the fork, the parent and the child will both have a descriptor table with an entry that points to the same entry in the system file table. What happens then is one of the values in the entries for each of these 2 kernel tables, the file table and the inode table, is a counter. Whenever a process opens an inode or opens a file, that counter is incremented. When a file is closed, the counter is decremented, and the entries are only removed from each of the tables when that counter or that reference count becomes 0. So that's a little bit of a background about the file descriptor table and a file pointer structure and the relationship of the descriptor table with the system file table or open file table and the system inode table or active inode table. And the key for this discussion is how this relates to the fork process with parent and children sharing files that are open prior to the fork, and also about the addition of a socket descriptor that again is identified by a positive integer value, which is the index into the descriptor table.